Hello, everybody. Today I'm going to be talking to you about a project that I've recently worked on titled Manipulation of Haptic Sensation During Bimanual Coordination. In the current experiment, we wanted to understand how haptic feedback influences parameters of movement during bimanual coordination. Bimanual coordination is an important problem to study because we utilize our limbs and our bodies in many different ways to achieve important goals. Additionally, it's important to simulate different kinds of environments that we may be moving around in, because this will allow us to understand how to improve efficiency in a wide variety of scenarios. You might think of oil workers working in deep sea trenches, moving around in underwater environments. Or you might think of patients who are undergoing rehabilitation and who work with elastic-based forces to regain control of affected limbs in fitness and physical therapy environments. One thing that's really cool about movement science is that we have the tools that allow us to simulate many different kinds of environments, and we can use something called a kin-arm robotic exoskeleton to do that. So in this picture, this is me on the left here. I am sitting in a kin-arm robotic exoskeleton when we first received it. And basically, this is a large robotic chair that participants sit in. You place your arms in these bins, and you're pushed into this environment where a LED TV is projecting an image onto a glass screen, and you can move your arms around underneath the glass screen as you see visual objects, and you can interact with these objects. And as you're interacting with these objects, you can apply forces to different parts of the limb to change the way that you interact with these stimuli. So to quickly situate the context of our current study, I'm briefly going to go over a paper that is foundational to understanding bimanual coordination. So in 1979, Kelso and colleagues ran an experiment where subjects were asked to move their fingers from specific keys, and movement parameters such as reaction time, movement time, and response time were studied, while speed accuracy trade-offs were manipulated through the size of the targets that subjects were asked to reach. And what they found was that humans will usually synchronize the movements of their limbs, even if targets are of unequal distances away from the start position, and subjects will also synchronize their limbs across levels of difficulty. This is seen not only in small differences between the limbs within the time course of movements, but is also demonstrated by the synchronization of peak velocities and synchronization of peak acceleration during these movements. So to demonstrate some of these measures, I've created some very simple visualizations to show you. So reaction time is operationalized as the time from stimulus onset, when the target is first initially displayed, to movement onset, which is defined as 5% of peak velocity per trial. Movement time is defined as the time from movement onset to the end of movement, where the target is reached. And total response time is defined as the combination of reaction time and movement time. So what happens when forces are introduced? What happens to these movement parameters and the synchronization of bimanual coordination when we introduce forces? So when we add viscous loads, as velocity increases in any direction, velocity-based loads are applied and become stronger, which makes it much more difficult to move quickly. We can generally hypothesize that this will increase time-based parameters, but we don't have any intuitions about how this would affect synchronization between the limbs. And when we add elastic-based loads or elastic forces, as the limb moves further from the start target, a spring-like force will pull back on the hand, and this increases in intensity the further the limb moves away from the start target. Again, we generally hypothesize that this will likely increase time-based parameters of movement, but we didn't have any intuitions about how this would affect synchronization between the limbs. So how we parameterized this question was through use of the kin-arm robotic exoskeleton, in which you can apply physical forces to the hand, the elbow, and the shoulder, and all you have to do is supply the equation. What we did was we ran 35 participants whose ages ranged from 18 to 29 years. These subjects were taken from our university's SONA subject pool. Specifically, we were interested in modeling viscous forces and elastic forces, and we applied these forces just to the hands. The image on the right up above me, depicts the subject's environment and where the stimuli were located. On the bottom, you can see the left and the right hand speeds of each reach for this particular subject in this specific reaching condition. In addition to loads, which is the force manipulation here, we also manipulated the distance of the targets, where targets were unequal distances away from the start position. And we also increased the level of forces through a difficulty index. The movement parameters of interest were reaction time, movement time, total response time, and velocity and acceleration measurements. So what actually happens? Let's take a look at some of the results. So here, I'm showing you total reaction time, which, if you remember, is the time from stimulus onset to movement onset. And this is separated by distance conditions and across load conditions. There's a lot of numbers here. So we have descriptive statistics of this parameter, but what does this actually tell us about synchronization between the limbs? So what is important to look at here is the difference or the delta between each hand. So the larger the delta, the greater degree of desynchronization there is between the limbs. The smaller the delta, the greater the degree of synchronization between the limbs. So what we see here is that when distance is equidistant for each limb, we see a very small degree of difference between the limbs, indicating that the limbs are synchronized while they're doing the reaches. When we manipulate distance, we find a greater degree of desynchronization between the limb, as indicated by this increased difference between the limb. We can also look at these relationships between the limbs statistically by modeling reaction time as a function of some fixed effects and some random effects. The random effects that we specified here were participants and trial number, and the fixed effects that we specified were the hand, the type of load or the force, and distance manipulations. What we found was that all load conditions or all force conditions significantly were different from the neutral condition. So forces significantly influenced reaction time. We also found distance significantly modulated reaction time. But what's interesting and important to look at here in order to understand desynchronization is to look at interaction effects between the hand and our other manipulations. So what we found was that when loads are different, when an elastic force is applied to one hand and a viscous force is applied to the other, the difference between the hands' reaction times are marginally increased. When the loads are viscous, and viscous being applied to both hands, the difference between hands' reaction times are marginally increased as well. And when the loads are elastic being applied to both hands, the difference between the hands is significantly increased. And when distance is manipulated, the difference between the reaction times is significantly increased. We can also take a look at movement time, and what's important to look at here is the delta or the difference between each hand. And what we see is that when the limbs are reaching equidistant targets, we find that no loads or no forces being applied to the arms has a great degree of synchronization. We also see a great degree of synchronization for the viscous loads being applied to both hands. However, this degree of synchronization is completely changed when we manipulate distance and also when we apply elastic or different loads to each hand. We can also look at this relationship statistically using the same kind of statistical model, just including movement time as the parameter that we're interested in. What we find for movement time is that different loads in general increased movement time. Elastic loads marginally increased movement time, and viscous loads significantly increased movement time. We are interested in the interaction effects here to understand synchronization between the limbs, and we find that elastic loads, when being applied to both hands, this marginally increases the difference in movement time between the limbs. So we see a little bit of desynchronization when we apply elastic loads to each limb. And all distance manipulations significantly impacted the movement time between limbs. We can also look at total response time as our measurement variable. Looking at the difference between each hand, we see the same relationship here in total response time that we saw before in movement time, where no load manipulations during equidistant reaches have a really high degree of synchronization. We also see a high degree of synchronization when viscous forces are applied to both hands. But in every other condition, when distance is manipulated, this significantly impacts the rate of synchronization between the limbs. We see a high rate of desynchronization. And when elastic loads are applied or different loads are applied to both hands, we find a higher degree of desynchronization between the limbs. We can look at this relationship statistically as well. And what we find here is that actually loads or forces in general don't have a significant effect on total response time. But we do see different loads, looking at interaction effects here, have a marginal increase on the difference in response times between the limbs, indicating that for this load manipulation, we see a higher degree of desynchronization. When elastic loads are applied to both of the limbs, this significantly increases the difference in response time between the limbs. And all distance manipulations significantly affect the difference in response time between the limbs. Another measurement variable that we were interested in was the time point of peak velocity, which is where peak velocity occurred during the trial. And what we find here is different load types being applied to the hands in general tends to increase the time point of peak velocity, meaning that it takes subjects a little bit longer to reach the targets when different loads are applied to the hands. Elastic loads marginally reduce the time point at peak velocity, meaning they're a little bit faster in the elastic condition. And viscous loads significantly increase the time point at peak velocity, meaning they're a little bit slower. This in general makes sense because viscous forces, the faster you try to move, the harder the force will push back. So it should take them a little bit longer to achieve peak velocity per trial. The interaction effect here is what we're interested in. And what we find is that distance significantly impacts the difference between hands for the time point at peak velocity, meaning that our distance manipulation desynchronized the limbs. We also can look at these relationships for the time point of peak acceleration. And what we find is that all load types significantly decrease the time point of peak acceleration. Distance significantly increases differences between the hands for the time point at peak acceleration, meaning our distance manipulations desynchronize the limbs. So, do we observe synchronization between limbs, and did we replicate Kelso and colleagues' experiment in 1979? Not exactly, but the study was inspired by Kelso and colleagues, and this wasn't a direct replication effort. What we did observe was decoupling between the limbs when distance was manipulated across all dependent variables, even in the no loads or when no forces were applied condition, in our control condition essentially. And this effect may be explained by two explanations. The first is that our control trials, what we also call null trials, were being randomly interspersed between force trials. So subjects may have had some kind of top-down strategy prepared during distance and load manipulated trials, or movements were being made by elbow pivots. They were not being made by just wrist flexion or a finger flexion. And when you move from the elbow, you have a lot more range of degrees of freedom to account for in statistical modeling. So the fact that these movements were being made in an ecologically valid scenario could affect this relationship between distance and desynchronization between the limbs. So some ideas that we have for future directions are to run this study again, but to use different kinds of forces. There are a lot of different kinds of forces that we can apply. One that we are specifically interested in is using curl forces, where it kind of curls your hand in a specific direction. We could also adapt difficulty of forces for each subject. One thing that I didn't mention is that we did not include difficulty as a fixed effect in our statistical models. And that was because our statistical model found that the level of difficulty was actually highly correlated with other fixed effects that we included within the model, which impacts the way that our model can assess these kinds of relationships. So we couldn't include it. There are some ways that we can account for that, and one of them is through Bayesian modeling. That takes a lot of computer power in order to do that, but that is a direction that we are looking into. And something that we could do is make sure that participants are feeling the same kinds of forces. So people have different levels of athletic ability, and this could impact the way in which they experience difficulty. So we could adapt difficulty of forces for each subject so that each subject is feeling something similar subjectively. We also plan on running this again, but we would like to put null trials or control trials at the beginning and at the end of the experiment to understand adaptation effects. And we're interested in investigating this effect between left and right-handed participants. There's some evidence to suggest that handedness may affect the way in which time-based parameters of movement are measured. And we also have elbow and shoulder joint data. We'd like to look at these areas of movement to understand if these areas of the limbs are being affected in terms of desynchronization in the same way that the hands are. All right, so if you have any questions for me, feel free to send me an email. My email is located on my website in the contact information section. All of my code is uploaded on GitHub. The data are also uploaded on GitHub as well if you'd like to play around with this data set. I look forward to hearing from you. Thank you very much.